this atom, the Rutherford's atom, can't stand for long. This is what E equals mc squared means. Lamai, this equation says, actually, right, mass is the condensed energy. The energy of a wave is carried by stream of energy packets, stream of particles, smallest tiniest particles, energy packets, the photons. He named those energy packets as photons. What is his idea? He said, okay, if appropriate conditions, waves can behave as particles, then the particles like electrons should also can be considered as waves. Good evening, Lamai. Right, let's start this today's session. Right, today actually we are going to discuss about the atomic models. Right. Okay, let's start the stuff. Right. Okay, this is continuity in the story of the atom. Right. Last day, actually, we have completed the discussion about the positive rays, finding of the fundamental positive charge. Right. So up to there, we have discussed the theory parts. Right. So today we are going to discuss about the atomic models, right? Okay, let's start, right? It's like this, Laman. So after finding those charged particles inside the atom, right? The scientists thought about how these charged particles are to occupy the atom. How these charged particles are inside the atom, how these guys are occupied in the atom. They thought about those, right? So with that idea, they came up with actually 5 atomic models, right? The first atomic model is to be discussed by the Thomson. Thomson was the first scientist who came up with the atomic model, right? The Plum-Tuddy model. After that, there were 4 models, right, up to the modern atomic theory, right? So we'll discuss about those 5 atomic models one by one, right? So all started with the Thomson's Plum-Tuddy model, right? Let's start the discussion with the Thomson's Plum-Tuddy model, right? Okay, so Thomson's Plum-Tuddy model. This is done by the G.G. Thomson, right? Basically in 1899, right? In 1899, Thomson came up with the first idea of atomic model, right? It is like this, Lama. The concept is very easy to grab, right? The point is actually the Dalton's atom was like this, no? Dalton's atom was like this. Dalton's, which normally came up with 1800s, right? Dalton's atom was like this. So it is known as a hard sphere or rigid sphere, the golf ball model. Golf ball, the kind of a hard or the rigid sphere. That was how the Dalton's atom looked like now, right? So Thomson came up with a very simple idea. Basically, after finding the electron, what he had done was actually he introduced those electrons to this hard sphere. To this hard sphere, he introduced the electrons. Basically, he introduced the electrons. Actually, he embedded the electrons, right, on the surface of the hard sphere. On the surface of the hard sphere, he embedded the electrons, right? So this is the Thomson's atom, right? So this is Thomson's atom, and he said further he added that as we all know the atom is neutral, right? So that this one should be neutral, so that the sphere should be positively charged. The sphere should be positively charged. That was the idea, right? A uniformly distributed positive charge should be there with the sphere, right? As the atom is neutral. That is the idea. Very simple idea, right? So what he had done is actually he embedded the electrons. I'll put it as the minus charge, right, like this. So he embedded the electrons on the surface of the atom, right? That is the idea. So he came up with this kind of a model, right? So this is known as actually plum pudding model. Plum pudding model. It's like a pudding which is with plums embedded on it, right? Plum pudding model by the Thomson. Thomson came up with this idea in 1899, right? Almost 100 years after Dalton came up with the first idea of atom, right? This is known as the plum pudding model, right? This is the first atomic model. Actually, this is the first atomic model which is with the subatomic particles. The first atomic model came up with the subatomic particles, right? It's actually Thomson's plum pudding model. The idea is very simple. You have the hard sphere, and the electrons are embedded on that thing. As the atom is neutral, the hard sphere should be with a positive charge, uniformly distributed positive charge. That is the idea, right now. So we'll go to the note and complete the note, right? Okay, note says like this. Just go to the note, Lamai. Right, the plum pudding model in 1899, right? Chris, did you get the tute? I think today. So, are you with the, PDF?
They have already sent it to me.
Okay.
Maybe it will be on the way there. So it will come maybe tomorrow. It doesn't matter. I can manage it today.
Okay, right. Sorry for that, right? Okay. Right. Okay. So let's continue then, right? The note says like this, right? It says the first atomic model was introduced by J.J. Thomson in 1899, and it was named as plum pudding model of the atom. It was named as the plum pudding model of the atom, right? And then it says this model was proposed soon after the discovery of electron, but before the discovery of the atomic nucleus. Remember that this was proposed after the discovery of electron, but before the discovery of the atomic nucleus, right? Okay, the model is this, right? And there you have a space. At that space, just write this one, right? Within inverted commas, right? In red color, just write this one, right? Quickly, right? Like this. An atom consists of numbers of electrons. An atom consists of numbers of electrons. This is what this model says means, right? An atom consists of numbers of electrons embedded in a sphere of uniform positive charge. Embedded in a sphere of uniform positive charge. An atom consists of numbers of electrons embedded in a sphere of uniform positive charge. Embedded in a uniform positive charge, right? That is the idea of this atom, right? So you have numbers of electrons embedded. Note that these electrons are not inside the atom, right? According to Thomson's model, the electrons are not inside the atom. Those are actually at the surface of the atom. So that is very easy to eject those electrons, no? With the ideas of that static electricity and the stuff, right? Thomson came up with such a conclusion, right? So he had seen that electrons are removing from the cathode as well. From the cathode surface, the electrons were removed as cathode rays, right? So with those ideas, with those observations, he had concluded that atom consists of numbers of electrons which are actually embedded on the surface of the atom, right? Not inside the atom. If such a question was there, according to the plum pudding model, the electrons are inside the atom. So if such a question statement was there, that is false. That is false. Get the idea, right? Electrons are not inside the atom. Those are just at the surface of the atom, right? Electrons are embedded on the surface of the atom, right? That is the idea according to the Thomson's model, right? So that is the idea, right? So the atom should be, the hard sphere, the rigid sphere should be with a positive charge as the atom is neutral. That is the idea. So you can draw this picture. This is the Dalton's thing, and this is the Plum-Body model. So draw the picture, right, and we'll mark the things as well, right? So this is the hard sphere, and you have the electrons embedded on it, right? Just quickly draw the picture as well, now. Pinturet draw karagannada, right? So the idea is you have, right, a positive charged sphere, right? So and a negatively charged electrons, right? This is the concept, right? So Thomson related these things to this thing to the pudding, right? This was the pudding, Plum-Body model. These are the plums, according to Thomson, right? This is just a simple idea, right? So just quickly draw the picture there, right? Okay, no? Or even you can come up with a screen capture, right? So we can continue, right, quickly, right? So this is Dalton's golf ball model, and here you have the Plum-Body model of Thomson. Very simple idea, right? He just embedded what he had found from those cathode ray experiments, right? The electrons, just embedded the electrons on the surface of the golf ball actually. That is the idea. Surface of the hard sphere, you just embedded the electrons. So as the atom is neutral, the hard sphere should be positively charged, uniformly distributed. Positive charge is there with the hard sphere. That is the idea, right? Okay, let's continue. Right, at the next point it says he further added that was there. Then write the next point. I'll just go through this stuff, right? These are very simple stuff, no? Right? Okay. Let's write like this within inverted commas in red color. Within inverted commas, just write the atom is neutral. The atom is neutral. The atom is neutral. The atom is neutral as the magnitude of positive charge in sphere, as the magnitude of positive charge in sphere, as the magnitude of positive charge in sphere, atom is neutral as the magnitude of positive charge in sphere is counterbalanced by the positive charge in sphere is counterbalanced by the negative charges of electrons. Counterbalanced by the negative charges of electrons. Counterbalanced by the negative charges of electrons. Right? No? Close the inverted commas. Right? So you can underline the phrase atom is neutral. You can underline the phrase atom is neutral. Because of the atom is neutral, the sphere should be positively charged. Right? The idea is that. Okay. That is all about the Thomson's Plum-Body model. Right now, let's discuss about the next model then. Right, and let's discuss about how this model failed. Discuss about how this model failed, and then how the next model formed. Right, this was the Thomson's model. Right, so at the next page. It is all about the Rutherford's experiment, the gold foil experiment. We'll discuss about that, right? Okay, the ideas are clear up to here, the Thomson's model, right? Okay, let's come up with the next stuff, right? Okay, next case. Now we are leading to the next topic. This is about the Rutherford's experiment, right? So Rutherford's nuclear model. Rutherford's nuclear model. That is the next model we are going to discuss, right? And first we will discuss about the experiment which led to this model, right? Rutherford's nuclear model, right? So it was actually constructed with Lehmann, right? Okay. So here we had introduced the nucleus. Concept of nucleus. Let's discuss about this model. Before that, let's discuss about the experiment, the very famous experiment led to this model, right? So the story is this. The story was this, right? So basically, Thomson had came up with this kind of model. No? Thomson had came up with this kind of model, no? Right? Okay. Then Rutherford and some bunch of scientists, Rutherford and his colleagues, normally not the colleagues, actually Rutherford and his PhD students, right? His students, right? Came up with a new kind of experiment, right? Came up with a good experiment to prove this model. Actually, the Rutherford and the Geiger and Marsden, the students of Rutherford, actually came up with a good experiment actually to prove this model. They, right, came up with a good experiment, right, thinking of proving this model, right? That is known as the alpha scattering experiment, right? Alpha scattering experiment, right? Or the gold foil experiment. The idea was this, right? They came up with some experiment, right? So they tried to detect some alpha particles. We'll discuss what those alpha particles are. Some let's at this instance just think of some matter particles, right? They came up with this kind of experiment. They came up with some alpha particles, the matter particles, and they directed those alpha particles to this atom, right? So if the atom is kind of this, kind of a hard sphere, if the atom is kind of a hard sphere, right? According to Thomson, if the atom is kind of a hard sphere, then what should happen? If the atom is kind of a hard sphere, then they expected those alpha particles not to go through the atomic layers but to escape back. That was the idea. If the atom is this kind of hard sphere, hard volume, is with the atom, they expected those alpha particles not to go through the atoms but to come back after hitting the atomic layers. After hitting the atomic layers, they expected those alpha particles to, right, come back. That was the idea of this experiment. But surprisingly, what happened was those alpha particles went through the atomic layers, right? So ultimately that led to the new atomic model, right? So that is the idea here we are going to discuss. Let's discuss the experiment step by step, right? Actually, the first idea was actually to prove this model, right? To prove this model, they have done this experiment, but ultimately the conclusion was the other way around. The theory failed, right? And a new theory or new model for the atom born, right? Let's discuss about this story of the atom, right? Okay, so it says, according to your note, right? Let's discuss about the full story, right? This is the normal idea, right? Let's discuss all the points associated with this experiment, right? Okay, go to the note, Lamai. It says like this. In 1909, Rutherford, together with physicists Geiger and Marsden, those are actually his PhD students, right? Geiger and Marsden, carried out a series of experiments using very thin foils of gold and other metals as targets for alpha particles from a radioactive source. Right? So that was the idea. See, this is now we are going to discuss about the Rutherford's gold foil experiment, right? Now that is the idea, right? Rutherford's gold foil experiment. This is also known as alpha scattering experiment, and is also known as alpha scattering experiment. the same experiment, right? Let's discuss about this experiment in detail, which led to the next atomic model, right? Okay, right. The thing is like this, Laman. They came up with this kind of a setup, right? They came up with this kind of setup, right? First of all, they had a very thin layer of atoms with a very thin metal, right? You had a very thin little metal. Basically, in this succeeded experiment, they came up with gold foil. Gold foil means very thin, right, layer of atoms, gold atoms, very thin layer of gold atoms, right? The gold foil, right? You came up with a gold foil, and basically you had kind of a radioactive source, which is actually covered by a shield like this for protection, right? So these are radioactive sources, right? So radiations are not good normally for human beings, right? So some covered stuff is there, right? So what they had done was actually they, as these alpha particles are releasing from here, right? Alpha particles will be directed to the, had been directed to the gold foil, and some screen was there. Some screen was there to detect the movements of alpha particles. Some screen was there to detect the movements of alpha particles. Right? That is the idea, right? Right. So it was like this, right? To detect the movements of alpha particles, right? They come up with a screen, right? So screen is there. So normally, which is actually painted from a fluorescent material, right? So what happened there, right? Alpha particles are detected like this. They expected actually to almost all the particles to bounce back. That was the expectation. If the atom is like the Thomson's model, if the atom is kind of a hard sphere, they expected almost all the alpha particles to come back, right? But what they have observed is the opposite of that. Almost all the alpha particles, right, went through the thin aluminium, went through the thin gold foil. Right? Almost all the stuff went through the thin gold foil. That was observed by some, right, glittering stuff associated with this fluorescent material, right? Shines can be seen directly opposite of the thing, right? So that they concluded almost all the alpha particles went through the gold foil without a deviation, right? Sometimes very with very low frequency, right, they had seen some of the things deviating too, but almost all the stuff are going through the foil, right? With a very low frequency, they had seen very few get deflected as well as came back, right? Very few, actually remember, very few came back or deflected, but almost all the alpha particles went through, right? They have monitored the deflections and the pathways of alpha particles by monitoring the glowings, right, appearing on this scintillated painted screen, right? Okay, that is the idea, right? So I'll just mark these things, right? So this is some fluorescent screen, right? So these are the beam of alpha particles, Actually, the alpha particles, what are these alpha particles? Alpha particles are actually the helium nuclei. Alpha particles are actually the helium nuclei. Remember that, right? In questions, they will ask those. Alpha particles are actually helium nuclei. Helium nuclei means, so the helium atoms are like this now. If you are copy the helium atom, you have +2 at the nucleus, right? And 2 electrons are there. This is the helium atom. So helium nuclei means after getting rid of these 2 electrons, after getting rid of these 2 electrons, what remains is the helium nucleus. So this is the helium atom. So the alpha particle is when you remove these 2 electrons. Just the helium nucleus. So you will see it is with +2 charge. This is +2 charge, right? So helium +2, that is known as the alpha particle. This is the alpha particle. So alpha particles are the helium nuclei, right? So some very small particles, so only the nucleus of the helium appears there with +2 charge. That is the nature of the alpha particles, right? So beam of alpha particles are actually helium nuclei, right? Right, no? So some positively charged particles, right? So you have a lead shield, and this is the radioactive source, right? This is the radioactive source which emits the alpha particles, right? And this is your thin gold foil. AU means gold foil, right? So very thin layer of atoms are there, and basically these are the observations, right? Most of the alpha particles went through the gold foil without a deviation, right? So most particles went through undeflected, right? Just change that word, Lamai. Some printing mistake is there with the word. Most particles are undeflected, right? And very few get deflected. Very few, right? Get deflected. These are deflected or scattered alpha particles, right? So this is the setup of the gold foil experiment, right? The main observation is almost all the alpha particles went through without a deviation, without a deflection, and very few alpha particles were scattered. That is the main observation with this experiment. And let's write those observations. Observations, just write the observations, right? Okay, because those will be asked in some MCQs, right? And the reasons are also asked, right? What are the reasons for those observations? Those will be also asked, right? Okay, right. First, write the observations, right? The picture is there in your note, right? So don't worry about drawing the picture, right? That is there in your note. But let's write the few observations they have seen, the major observation and the few other observations, right? So those will be known, and some questions will be asked as well, right? Okay, and we have provided you the workbook as well, Lamai. So go through the workbook as well, right? When we completed the section, always do the workbook stuff as well, right? I forgot to mention that thing in the last class, right? But keep it in mind always to complete the workbook when we are completing a section, right? So I'll send you the answers for the workbook as well, right? For the workbook, I'll send you all the answers, right? And check those. And if you have any doubts about the answers or any doubts, right, about the section, just feel free to ask at the next class, right? At the next class, just feel free to ask about the doubts which are appearing in the workbook, right? Always complete the notebook stuff until what we have completed, right? Okay, always carry that work, right? Okay, then I'll give you some little more time after the class, after 10:30. I'll give you 15-20 minutes, right, to discuss the things appearing at the workbook. If you have any doubts only, right? If you have any doubts, right, you can ask me, and I'll answer them at the end of the class for about 15-20 minutes, and also through WhatsApp also we can discuss the questions, right? So always keep in mind to complete the notebook until the sections we have completed, right? Always do that stuff, right? Okay, continuous working is very important in this case, right? In A-levels, right? Okay, this is the setup that is there in the note, right? We'll write the observations, right? So we have space there in your note at the page number 12, right? Let's complete the observations part there, right? Observations. First point, just right. First point. Point number 1, right? Majority of particles penetrated the foil either deflected or majority of particles penetrated the foil either undeflected or okay, without a deflection, right? Either undeflected or only with a slight deflection, or either undeflected, majority passed through the aluminium foil. Majority of particles penetrated the foil either undeflected or only with a slight deflection. That was the first observation, right? Second observations. We have seen 3 observations. Let's try the 3. Second observation. Few alpha particles were scattered within brackets or deflected close brackets at a large angle. Few alpha particles were scattered or deflected at a large angle. Right, at a large angle. Right. Okay, next one. Lamai, actually scattering. The two words are there, right? Deflection and scattering. What is the difference between those two? If you have to use the words correctly, there we are using 2 words there, deflection and the scattering, right? Deflection means you are changing the pathway, right? You are changing the pathway of travel. Right? That is deflection, right? But when it comes to scattering means you are not going through the thing. If some particle is not going through the material, means if you are bouncing back, coming to the same side of what you came up with, right, is actually known as scattering. You are not going through the material. That is scattering. So some scattered with a large angle, right? So that is the idea. Some scattered with a large angle, right? Right? No? Some undeflected particles are there, and some scattered with a larger angle, right? Actually, this is not good, right? This is not, and this should not be the one, right? This is deflected. This is just deflected, right? These are the ones which are scattered, right? These are the ones which are scattered. Scattered means you are not going through the material. Those are scattered. These are deflected, right? Just deflected. Scattering is also a kind of a deflection, but scattering means a special kind of a deflection. That means you are not going through the material. This is what is mentioned as scattered, right? Deflection is any situation where you change the direction of movement, right? That is the deflection, right? So 2 words, right? Okay. So next one, third point. very few alpha particles bounced back. Very few alpha particles bounced back in the direction from which it came. Very few alpha particles bounced back in the direction from which it came. Very few alpha particles bounced back from the direction from which it came. That point, right? Very few alpha particles bounced back in the direction from which it came, right? So let's summarize these ideas with a little picture. Let's summarize these ideas with a little picture here, right? So I'll come up with a little picture to summarize the observations, right? So at that space, you just draw this simple picture as well, right? Right. I'll draw that picture here, right? So when it comes to a thin gold foil, that means very few atomic layers are there. Thin gold foil, that means very few atomic layers are there. Very few atomic layers are appearing. Sorry, this is not straight, no? When it comes to gold foil, very thin atomic layers are appearing, right? This is one layer of atoms. When it comes to thin gold foil, very few atomic layers are appearing like this. This is just the picture, summarized picture of the observations, right? This is your thin gold foil. Few atomic layers are there. That is why we say it as thin. Right? What happened was actually you had a screen there, fluorescent screen. This is just a cross section of the experiment, right? Cross section when you are to look from here. When you are to look from here, this is what it looks like, right? So you have a screen here, right? So let's see. Let's look from here, right? Thin layer of atoms and the screen here, right? Okay. So the point is like this, right? This is the fluorescent screen. Right? This is how the alpha particles travel through the atomic layers, right? Almost all the alpha particles travel through the thin gold foil like that. Right? But sometimes they had bounced back like this as well. But most of the stuff travel through without a deviation. With some stuff, some slight deviations were also there, but almost all the stuff travel through without deviation. This is just the observation, right now? Okay, just draw this stuff, Lamai. Just draw this stuff. These are alpha particles. Right. Okay. Quickly draw this one at the space given for the observations. At the page number 12, you have such a space, right? Thin gold foil is there, few atomic layers, right? So basically almost all the stuff went through the atomic layers. Right now, so you can take a screen capture as well, Lamai. Just go for a screen capture, then it is easy now. Right now. Okay, let's discuss about the conclusions. What they have made after seeing these observations. After seeing these observations of almost all the stuff going through the foil, right? Let's discuss about what observations, what conclusions are made from these observations, right? Okay, actually they came up with three. They came up with three conclusions. They came up with actually three reasons. They came up with three reasons for these three observations. For these three observations, they had came up with three reasonings. Let's discuss one by one. After that, we can write. The first thing. The first thing. The most important reason. Right? It is that. Right? That is actually they have seen almost all the alpha particles are going through the thin aluminum foil now. Right? They give a nice reasoning for that thing. Such an observation appears, almost all the alpha particles are going through the thin foil. So such observation appears, right? They are saying that such observation is will be appeared because almost all the space of the atom is empty. Because almost all the space of the atom is empty, you would be able to see almost all the alpha particles are going through those atoms. Right? That is possible only if the almost all the space of atom is empty. The idea is that no, right? Let's discuss a bit more about that thing. Right? It's like this now. Right? When you have a atom like this, right? This was the atom, right? With the Thomson's atom, here and there the electrons were there. With the Thomson's atom, here and there the electrons were there. But the atom was like this, no? It was a hard sphere, no? Hard rigid sphere, no? According to Thomson. Right? Here and there few electrons were there. Right? This was the Thomson's atom. But if the atom is to appear like this, the alpha particles can't go through that. It should come back. Right? But they are saying, that scientists are saying now, this atom is empty. Almost all the space of this atom is empty. It is not a hard sphere. That is empty. That is why you are able to see this observation of alpha rays penetrating without a deviation. Right? No? That is possible only if almost all the atom is empty. Right? That is the idea. So almost all the atom is empty, space of the atom is empty, you are able to see this kind of observation of penetrating almost all the alpha particles, right? Actually going through the thin foil. That is the idea, right? That is one conclusion made by the first observation. And then what happens to the mass of the atom? If the atom, all space of the atom is empty, what happens to the mass of the atom? They are saying that mass of the atom is concentrated to the center, like this. Concentrated to the center, like this. Almost all the mass, almost all the space of the atom is empty. Then the mass is concentrated to the center, to a very small space at the center. That is where all the mass is there. Right? The point is this, Lama. So Actually the Thomson came up with right. Thomson came up with the atom, right? This kind of a mass. Thomson came up with this kind of mass as the atom. Then what Rutherford said was, no, the mass is not throughout the space of the atom, but it is concentrated. It is concentrated to the center of the atom. This whole stuff, the mass is concentrated to the center of the atom. So mass appears only at the center of the atom. All the other space of the atom is empty. That was the conclusion made up by seeing this observation of all the particles going through the atoms. Right now? So that is the first thing. That is the reasoning for this observation of almost all the other particles going through the thin layer of atoms, right? Okay. Then some more reasons are given for these two deflected situations. They have said this kind of a thing is possible. This kind of a thing, so some slight deflection. That slight deflection is possible when the alpha particles are going near to the center of the atom. When the alpha particles are directed and coming to this center of the atom, closer by, right? Then you see this kind of a deflection only if the center is positively charged. The center is positively charged. They are saying, right, this kind of a deviation is possible, right, as alpha particles are also positively charged helium nuclei, right? So this thing should be also positively charged. This thing should be also positively charged. Then only this kind of a deflection is possible. That is the second thing. Almost all the atom space of the atom is empty. That is by the first observation. And then with the slight deviations, they have said that deviations are possible as this guy should be positively charged. This guy should be positively charged. So positive particles repel from the positive charges. That is how that happens, right? So that is the idea. So you have an atom, right? At the center, you have a positively charged mass. That is the ultimate idea, right? So what about the other observation? What is the reason for that thing? They are saying very few alpha particles are scattered or came to the same direction as they were origin, right? Because those alpha particles actually came directly to the mass. If those came directly to the mass, then they will bounce back. That is the idea. That is how they reason out the three observations they have seen. Almost all the alpha particles went through the atom because almost all the space of the atom is empty and the mass is concentrated to the center of the atom. That is the reason for the first observation. Then some very few alpha particles were scattered with a small angle. That is because this thing is positively charged, the mass is positively charged, and that is why the repulsion occurs with the alpha particles, right? So that concludes that that mass is positively charged at the center. And for the third observation, that coming back, the alpha particles are coming back, right? Because those were actually directed directly to the center, right? Okay, that was the conclusion. So that was the reasonings for those observations, right? Okay, and then ultimately this part is referred to as the nucleus. This part is referred to as the nucleus of the atom. At the center you had the dense mass which is positively charged. Ultimately it is referred to as the nucleus of the atom. That is how that nuclear model born. That is how the nuclear model born, right? Okay, let's write these stuff, right? The explanations and conclusions, right? They have made. We had discussed. Now we have to write those stuff, right? Okay, at the page number 13, just write these ones, right? These explanations, right? Okay, explanations and conclusions at the page number 13, right? Let's write. First point, right? First point, right? Like this. Most of alpha particles pass through the gold foil. Most of alpha particles pass through the gold foil, right? Most of alpha particles pass through the gold foil. Most of alpha particles pass through the gold foil with little or no deflection, with little or no deflection, with little or no deflection. Most of alpha particles pass through the gold foil with little or no deflection because write it in red color, write this thing with red color, come to red color opinion, right? Most of the atom must be empty. 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 Most of the atom must be empty, right? Most of the atom must be empty. Come to the normal color and write. Come to the normal color and write at the next line. At the next line, just write. So the positive charges of atoms. So the positive charges of atoms. So the positive charges of atoms are all concentrated in a. So the positive charges of atoms are all concentrated in a. So the positive charges of atoms are all concentrated in a dense central core. Dense central core. All the positive charges at the center, right? Concentrated in a dense central core. Dense central core called dense central core called dense central core called. Come to the red color, Lamai. Come to red color pen and write. Come to red color pen and write. Nucleus. 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 Again, come to the normal color, which is at the center of atom. Which is at the center of atom. Which is at the center of atom. Which is at the center of atom, right? That is the first explanation for the observation of most alpha particle traveling without deviation, right? Okay. The second point, second explanation, second point. Let's write this. When an alpha particle come close to the nucleus, when an alpha particle come close to the nucleus, when an alpha particle come close to the nucleus, when an alpha particle come close to the nucleus, when an alpha particle come close to the nucleus, it experienced a large repulsive force. It experienced a large repulsive force. It experienced a large repulsive force. Now we are thinking of this one, right? This one. When as the alpha particles are positively charged, it will experience some repulsive force. The positive charges will repel, right? It experiences a large repulsive force and therefore a deflection. therefore a considerable deflection, therefore a considerable deflection, therefore a considerable deflection, therefore a considerable deflection. Right. Next point on this, right? Next point, when they come direct to the nucleus, right? Next point, third point, right, like this. An alpha particle traveling directly towards the nucleus, an alpha particle traveling directly towards the nucleus, an alpha particle traveling directly towards the nucleus, an alpha particle traveling directly towards the nucleus would experience an enormous repulsion, would experience an enormous repulsion. An alpha particle traveling directly towards the nucleus would experience an enormous repulsion, would experience an enormous repulsion that could completely reverse the direction of the moving alpha particle. That could completely reverse the direction of, that could completely reverse the direction of, completely reverse the direction of the moving alpha particle, completely reverse the direction of the moving alpha particle. Right? That is this idea, right? When they are coming directly to the nucleus, they will bounce back, right? Because of that reason, right? Okay, no? That is, those are the explanations and conclusions, right? About the three observations, right? Then lamai, a few points are there with the note, right? Let's go to those things quickly, the few points, right? The first point, it says, right, with this experiment, Rutherford was the first scientist to discover the existence of nucleus. So actually, the concept of nucleus was born with this atomic model, right? Concept of nucleus was born with this atomic model. Earlier, there was no such thing as nucleus, right? With the Thomson's model, the positive charge was all throughout the atom. But here, now with this atomic model, it is said that the positive charge or all the mass of the atom is condensed in a very little space at the center, right? So that is known as a nucleus. So the concept of nucleus first came up with this model, right? So that is why it says, with this experiment, Rutherford was the first scientist to discover the existence of nucleus, right? So a nucleus is introduced with this model, right? Okay. Next point, it says, with the Lama, these things are at your book, right? I'm just going through the points there. With the use of deviation angles of alpha particles, then scientists were able to find that the nucleus of the find that the radius of the nucleus is about 10 to the power minus 15 meters. That is another valuable data. What is that? It is this, right? So that data says something about the size of the nucleus. Something about the size of the nucleus. The point is this, Lamai, right? So basically, Lamai, right? Do you guys know the size of the atom? Actually, the size of the atom. If you have to take the size of the atom, the radius of the atom, right? It is actually the radius is comes with some 10 to the power minus 10 meters. Normally, atomic radii are measured with angstrom units. Normally, atomic radii are measured with angstrom units, right? Angstrom units, right? Angstrom units. Angstrom means 1 angstrom means 10 to the power minus 10 meters. So basically, atomic dimensions or atomic distances are measured in angstrom units. It is smaller than the nanometers. It is smaller than the nanometers actually, right? That is the idea, right? So atomic radius is this. right, into the power of 10 to the minus 10 meters. But for the radius for the radius of the nucleus, it is actually with 10 to the power minus 15 meters. With 10 to the power minus 15 meters. Very small, right? Very small, right? Get that idea. The volume of the nucleus is very small compared to the volume of the atom. Compared to the volume of the atom or the size of the atom, the size of the nucleus or the volume of the nucleus is negligible, very small. So all the positive charge is concentrated to that small point at the center. That small point at the center of the atom, which is referred to as a nucleus. So remember that it is very small, right? If you have to take that idea seriously, it is like between these two guys, some radii difference of 10 to the power 5 meters appearing. Between these two guys, 10 to the minus 10 and 10 to the minus 15, this amount of difference is appearing. That means this is actually 10 to the power 5 meters means this is actually, right, 1000, this is actually 1000 kilometers. This is actually 1000 kilometers. Got the idea? So 10 to the power 3 means kilo. We have 10 to the power 5, so all together, right? 100 kilometers. Sorry, the 100 kilometers. This is actually 100 kilometers. See? So it is like that. If you are here at the nucleus, your border of the atom, the margin of the atom is situated, right, from 100 kilometers from you. That is the idea, right? You won't see the margin of the atom if you are to stand on the nucleus. Such an idea. Very small, tiny space with the nucleus, right? So that is the idea of how small this nucleus is, right? Okay, I think you got the idea, right? So anyway, the radius of the nucleus is 10 to the minus 15. The radius of the atom is kind of 10 to the power minus 10, right? No? Okay. So third point, it said, with the finding of gold foil experiment in 1911, Rutherford put forward his atomic model. Let's draw this picture there. Let's draw the picture of the Rutherford's model as well. Earlier we had drawn the picture of the Thomson's model, no? Thomson's atom, no? Plum-Pudding model. Now let's draw the picture of the Rutherford's atom, right? The picture is this, right? So you have the positively charged nucleus at the center of the atom, right? And here and there the electrons are appearing, right? Now it was like this, so basically with the Thomson's model, this was the Thomson's model, no? Right? Thomson's model was like this, no? Electrons were there, and this, right, this stuff was positively charged, no? Positively charged sphere, no? This was Thomson's model, no? This is Thomson's atom, right? So you had a positive charge sphere, and some electrons. This was Thomson's atom in 1899. Plum-Pudding model. What Rutherford does was actually very simple change done to the model. What he did was actually, right, he actually concentrated all this mass, all this positive mass to the center. He concentrated all this positive mass to the center. Concentrated all the positive mass to the center, which is known as the nucleus. This whole positive mass was centered as the nucleus, right? All the mass is there, right? So that is centered and called it as the nucleus. That was the only change done by the Rutherford, right? So this is your, right, positively charged nucleus. Right, and the electrons are still there, right? Electrons are still there. All the positive mass was concentrated to the center, right? That is the idea, right? So this is Rutherford's model. This is Rutherford's nuclear model. This is known as the nuclear model, the interaction of the nucleus. Rutherford's nuclear model, right? Which was actually done in 1911. I mean, just draw this picture, right, of Rutherford's atom. Right? Just draw both the pictures, right? So earlier Thomson's case was like this: positively charged hard sphere, right? But Rutherford came up with a very slight change, right? That he said that all the mass is concentrated to the center. That is the only change he had done to the Thomson's model, so that the nucleus is born, and that is the nuclear model. Right now, just come up with those two pictures, right? This is Rutherford's nuclear model. At the center, the mass is there with a positive charge. Right now. Right now, let's complete the stuff, right? This is how the nuclear model was born, right? This is the second atomic model, right? The nuclear model. With this model, the concept of nucleus born, right? This is the first model. This is the first model with the nucleus. This is the first model with the nucleus. Right now? Okay. Let's discuss about the failures of this model. Let's discuss about the failures of this model, right? Actually, two failures were there. Two failures were there with this model, right? Let's discuss one by one, right? Okay. First one, I'll first write the we'll discuss the two failures, right? Then we'll write. Two failures are there, right? First thing, actual lamai, this atom, the Rutherford's atom, can't stand for long. This atom can't stand for long. This is very unstable atom. Rutherford's atom is very unstable, lamai. Right? This kind of a thing is okay, lamai. You have positively charged sphere. The oppositely charged electrons are stick to that sphere. That is acceptable or not? The positive charge sphere is there. The negative charge, the opposite charge particles are stick to that positive charge. Because of the attractions that will happen, attraction between the opposite charges, that will happen. This is okay. But when it comes to these, right, you can't think of this kind of a model appearance for a longer time, no, Lamai. Why is that? Because, right, you have a space in between. You have a positive charge here. You have a negative charge here. This negative charge will surely attract to the positive charge, no? These negative charges will surely attract to the positive charge, no? And then they will fall to the nucleus and combine with the nucleus and neutralize the nucleus, no? That is the idea. So as we are with some space between the nucleus and the electron with this model, and these two particles kinds are with opposite charges, definitely these negative guys should attract to the positive charge nucleus or should fall into that nucleus, and ultimately the charge of the nucleus should neutralize. So this atom can't stand for long with this conformation. With this conformation, this atom can't stand for long, so that this atom is considered as kind of an unstable atom. So atom is unstable according to this model. Atom is unstable according to this model. So unstable. I think you got the idea of stability, stable, unstable thing. Anyone? Can anyone tell me what is meant by stability, stable? What you feel when you heard the word stable? Right? What is the idea of stability? Stable? Yes, anyone can give me what is meant by stability? Stable. Sometimes we say we are stable now. That thing is stable. That guy is stable now. His words are very stable. Right? Actually, what is the meaning of that word stable? Anyone? Yes. Sorry? Net charge is zero. Yeah. Net charge is zero. But actually, that is, yeah, according to science, you can think of such a definition. But what do you think that what will be there at the Oxford, right? What do you think? Are you think that Oxford dictionary says that the stable, with that word stable, do they come up with such a definition? Net charge is zero? No, I don't think so. Right? What kind of explanation would be there for that word stability? The English word stability. Stable. Stable means any other try? Yeah, you can try for another time. Permanent. Oh. So, comes closer. The point is this, Raman. I'll tell you the actual meaning of stability. Stable. Stable means you are not changing for a longer period of time. If something is not changing for a longer period of time, we can say such a thing is stable, right? If some discussing stuff, right, is not changing for a longer period of time, we say that thing is stable. That can be applied for a particle, that can be applied for a human being even. Okay, that can be applied for some ideas. We can say his ideas are very stable, right? That means he is with the same idea for a longer period of time. He said the same thing for a longer period of time. Even today, even after 1 year, even before 1 year, still he is saying the same thing. He is very stable. His ideas are very stable, right? So stable means actually, right, if the concerning stuff is not going to change for a longer period of time, we label them as stable, right? Okay, so not going to change for a longer period of time. If something is appearing without a change for a longer period of time, that means those are stable. If not, those are unstable. If not, those are unstable, right? Okay, that is the idea. So you clearly see this atom is unstable. This atom is unstable because you can't be with this conformation for a longer period of time. Basically, with the other instance, next instance, these electrons will combine with the nucleus, fall into the nucleus, and this atom, this concept collapse, right? So this can't stand for a longer period of time. That means this is unstable. This is not stable, means unstable, right? So the atom is unstable according to this model. According to this model, the atom is unstable. That is the main problem with this model. Actually, that is the main problem which inspired scientists to come up with a other model, new model, right? Okay, that was the first failure, and we had another failure. They had another failure, right? Two failures were there with the Rutherford's model. The second failure was this was unable to explain the atomic spectra, the hydrogen spectrum and the atomic spectra, right? This was unable to explain, right? Those ages in 1911 and those ages, right? That was a huge problem in science, right? In those areas, basically from starting from mid 1800s, right? 1815s, 1850 to uppers, right? There was a huge problem which is unanswered, without an answer, right? That is actually with the hydrogen spectrum. They have seen kind of a specific spectral lines and a spectrum, right, with the hydrogen atom, originated from the hydrogen atom, and the scientists were without any clues or without any answers for the origin of that hydrogen spectrum. And that was a kind of a major problem to answer at those ages, right? And then after that, actually that hydrogen spectrum was found in mid 1850s, right? But this model came up after that. Still, this model was unable to explain the hydrogen spectrum. So this model was unable to answer the biggest problem at that ages, right? At that age, right? So that was another failure, right? If you had came up with a good model, you should be able to answer the problems existing, right? So this was unable to answer that huge problem of the hydrogen spectrum, the origin of hydrogen spectrum, right? So that was the second failure, right? So those are two failures, and the next model, which we are going to discuss, is the Bose model. That model came up with two good solutions for those two problems, right? The Bose model, next model, came up with very good two solutions for those two problems, right? And we'll discuss that model later. First of all, let's write the two failures of this model, right? Okay, at the page number 13, at the bottom part, it said, right, failures of Rutherford model. Let's write the two failures of Rutherford model. Number one, just write this stuff. Number one, according to this model, the atom is unstable. Now I write it in red color. The atom is unstable. Write it in red color. That was the first failure of this model. According to this model, the atom is unstable. Right. That was the first failure. The second failure, number two. It could not able to explain the theory behind it could not able to explain the theory behind. Write it in red color. Hydrogen spectrum. Theory behind hydrogen spectrum come to the normal color, and other atomic spectra. And other atomic spectra. Hydrogen spectrum and other atomic spectrum. Right? Those are the two failures of this Rutherford's model. Two failures of the Rutherford model. Right now? Okay. It is done. Right? So before we are going to discuss about the next model, right? Before we are going to discuss about the next model, right, which is the Bohr's model, right? Bohr came up with good solutions for those two problems. Now, before we are going to discuss about the Bohr's model, let's discuss a bit about the electromagnetic radiation. Let's focus on discussion of electromagnetic radiation, because without the knowledge of electromagnetic radiation, we can't grab the ideas of Bohr, right? Actually, the ideas of Bohr which came up to explain the hydrogen spectrum, right? So basically, the hydrogen spectrum is explained with the ideas of electromagnetic waves, right? So to clearly grab those ideas about the electromagnetic those ideas about the hydrogen spectrum, first we should know how these electromagnetic waves are behaving. So let's focus our knowledge, our discussion towards electromagnetic waves. After learning about the properties and the stuff about the electromagnetic waves, then only we will go to the solutions to these two problems and the Bohr's model, right? Okay, let's come up with a discussion of the electromagnetic waves, right? Let's come up with that. Before that, Lamai, do you have any problems, anything which you need to ask about the discussion so far? Do you guys have any questions before we are going to the electromagnetic waves, that section, right? Any questions, Chris? Or
model, the plum pudding model, sorry, it's just a imaginary model, no? Because it, without any experiment, no? After find the electrode, no?
Yeah.
But after Goldfield, Goldfield experiment only, they were able to find this the other model, no? Based on that only, they found the other model where the nucleus model, no?
Yeah. That is the idea. So actually, plum puddle model is without any experimental evidences, right? So basically, after founding the electron, what Thomson did was just embedded those electrons on that Dalton sphere. That was a simple idea. Dalton had a hard sphere, right? Just Thomson embedded those electrons on that sphere. Then, as the atom is neutral, he said that sphere is positively charged. That is the plum pudding model, without any experimental evidences. Actually, Rutherford and Geiger and Marsden, those guys started their experiment to prove this model. The Rutherford and the Geiger and Marsden started their experiment, the Goldfoil experiment, to prove this model. Actually, the experimental evidences and the observations went to another direction. But the idea was to prove this model, but ultimately they come up with a very new model, right, by the experimental observations. Those such things will be more frequently seen in science, Lamai. So they started doing some experiments to prove something, and they come with the observations and the things of the experiment, they come up with another new stuff, right? That is normally happening with scientific experiments, right? Yes, that is the idea. So by the experimental evidences, by the Rutherford's Goldfoil experiment, they come up with the nuclear model. Yeah. Any other questions you have? Yes, Utuni, do you have any questions regarding the stuff we have discussed so far? Yeah, okay, welcome. Not much. Yes, Lama, this is kind of an interactive session, right? So you can ask any questions, right? Uh, Basically, at the end of the class also, I'll give you some 15 minutes to ask any question regarding chemistry, right? So that will be a bonus for you, right? Even not from the stuff we have discussed so far, even you have learned some more stuff from anywhere, right? Still you can ask questions regarding them after the class. I'll give you 15 minutes, right? After the 10:30, I'll give you 15 minutes to ask any question regarding any stuff you have learned on chemistry. All right. If you have any questions, you can come up with the chat box as well. Yeah, so far that is clear. Okay. Right. So you can use the chat box as well. And as you two guys were not there at the first lessons, right? I have said that you can ask the questions in both the languages, right? I know the English and as well as Sinhala, right? So you can use both the languages, not the Tamil, right? Sorry for that. Anyway, yeah, all the questions are welcome, right? So by asking those questions only, you can learn the language. You learn the subject, right? So always I prefer asking the questions, right? Okay. Anyway, be prepared and be prepared with questions, right? That is very encouraging, right? I'm again saying you, right? You can ask any question after the class. After that, I will give you 15 minutes to ask any question regarding any of the stuff appearing in the chemistry, right? Not only with the stuff we have discussed, but if you have learned some more stuff from the school or from any other class, still you can come up with questions, right? So you can send me the questions to WhatsApp, right? Yeah, this is my WhatsApp number, right? So this is my personal number, right? So you can send any question to this one, right? Right? You can use voice messages as well, or you can put some screenshots of any of the questions, right? So pictures of question papers even, right? So use this number to ask any question regarding chemistry, even from the second units, if you have done so far in your school or anywhere else, right? Okay. So don't have any doubts with you. Always clear those doubts and go forward, right? That is what we expect, right? Okay. Right. Let's use that thing, right? That time of after the internet, right? For those questions, right? Let's come up with the next one, next topic. And you can use the chat box as well, right? It's written on, right? Okay. So if you haven't written that thing, just ask for my number from our supporting staff, right? Okay. Right. Next, let's come up with the next topic. This is actually about the electromagnetic radiation and atomic spectra, right? So we'll start the discussion on electromagnetic radiation now, right? Electromagnetic radiation. Next day we can learn about the hydrogen spectrum. Today we'll get the fundamentals, the foundation towards the study of the hydrogen spectrum, right? So this is electromagnetic radiation. Electromagnetic waves or radiation, right? Right. Let's discuss about this one. Electromagnetic radiation. Right. Okay. Few things to discuss here. Right. First thing is very clear, simple idea, right? So these are waves, no? Electromagnetic radiation, right? So these are waves, right? When it comes to waves, right? When it comes to waves, Lama, there are three main properties of a wave. There are three main properties: the velocity, the frequency, and the wavelength. The velocity, frequency, and the wavelength. those things are actually related through this equation. Those things are related through this equation, right? The V is equal to, right, F lambda. You may have learnt this equation in your O levels. The three properties: the speed or the velocity, frequency, and the wavelength. Those three properties of a wave is related with this equation, right? So when it comes to electromagnetic radiation, all the electromagnetic radiation travels with the speed of light, right? All the electromagnetic radiation travels with a constant speed, which is actually the speed of light. Before that, can you give some examples for electromagnetic radiation? Let's discuss a bit about that thing and continue this one. Yeah, Chris, can you give me an example for electromagnetic radiation? Some example?
Radio wave.
Radio waves. Okay. You started with the smallest one, right? Okay. Uttuli, some example for electromagnetic radiation? Yes, you can use the chat box as well. Some example for UV rays. Yes, of course, UV rays. So UV rays, right? X-rays, right? Then we have visible rays. The colors, green color, blue color, the colors there comes under visible rays. IR rays, the heat rays, right? So microwaves, radio waves, right? Those are the electromagnetic radiation, right? All of those electromagnetic radiations are actually traveling with a constant speed, which is known as the speed of light, So for all the electromagnetic waves, right? For all the electromagnetic radiation of waves, right? The velocity is equal to a constant value, which is known as the speed of light. It's a constant value, right? So we put that value with the symbol c. This is specific speed. So when it comes to other waves, not for the electromagnetic waves, the other waves like sound waves, right? Some water waves, waves are there, right? So for those, right, the speeds are not constant, they will differ like that, no? Right? But for all the electromagnetic waves, the speed is a constant, which is actually, what is the value there? Which is actually this value, 2.998 into 10 power 8 ms minus 1. This is the constant speed of all the electromagnetic waves, which is referred to as the speed of light, right? Speed of light, right? So for all the electromagnetic waves, you are coming up with a constant velocity. As it's a constant, we come up with a different letter there, right? Normally, with electromagnetic radiation, right, the frequency is mentioned with the letter mu. The frequency is mentioned with the letter mu. For all the waves, normally the frequency is written in F, right? The symbol F is used, but for the electromagnetic waves, the frequency is normally written in this symbol mu. For electromagnetic waves, the velocity is always the speed of light, c. The frequency is normally denoted in this symbol mu for the electromagnetic waves. Lambda is same, the lambda, wavelength is lambda. So you have a relationship between the wavelength, frequency and the speed, right, for the electromagnetic waves like this. C is equal to mu lambda, right? So this is the equation, right? C is equal to mu lambda, right? So speed of light and the frequency of radiation and the wavelength of the electromagnetic radiation. Actually, when it comes to the electromagnetic radiation, this relationship is very important. Even though you see this as a three-term equation, right? We are discussing about the electromagnetic radiation, so I'll erase this one, right? Okay. Even though you see this equation as a three-term equation, even though you see this equation as a three-term equation, actually we are only with two variables here. Actually we are only with two variables here, because this one is always a constant. This one is always a constant. C is always a constant for the electromagnetic waves, right? So that this is kind of a two variable equation. This is very important to see this equation like that. Two variable equation. Only two variables are there which can get different values. But this value is always a constant. So that we can say this equation gives you the relationship between the mu and the lambda. This is the equation which gives you the relationship between the mu and the lambda. Because C is always a constant, you always know this value. This value is given in your question paper as well. But you will know that value, right? 3 into 10 to the power 8, normally it is ultimately known as 3 into 10 to the power 8 after simplifying. So if you know the mu, this equation gives you the lambda. If you know the mu, this equation will give you the lambda, because C is always a known value. C is always a known value. If you know the mu, this equation can be used to come up with the lambda. If you know the lambda, this equation can be used to come up with the mu. Because C is always a known value, 3 to the power 8. So remember this. See this equation like that, right? This, even though this appears as a three-term equation, no, this is a two variable equation. Only two variables are there. If you know the mu, you can come up with the lambda. If you know the lambda, you can come up with the mu with the use of this equation, right? So it is very important to see this equation as a two variable equation. This is actually the relationship between the frequency and the wavelength of an electromagnetic wave, right? Okay, so let's go to the note, which it says, with the first point, it says, when considering electromagnetic waves, the relationship between their speed, frequency and the wavelength is as follows, and you better write this stuff at the given space. You can use all the space given there to write this one, right? Write it in big letters even. The C is equal to mu lambda. The speed of light, it's a constant always in a vacuum. It's a constant value in a vacuum, right? This is the value. Normally we take this one as 3 into 10 to the power 8. And this is the frequency of the wave, and this is the wavelength of the wave, right? This is the relationship between the frequency and the lambda actually, right? Because C is always a constant, right? Okay. Quickly put this thing there at this space, right? That is the first thing we need to know about the electromagnetic waves. The first thing we need to know about the electromagnetic waves, right? Okay. Right. Next one. Right? And when it comes to electromagnetic waves, few revolutionized ideas came from some famous scientists, right, about the electromagnetic waves at the start of the 1900s, right? At the start of the 1900th or 20th century, right? So few revolutionized ideas were put forward by very famous scientists, right? So let's go to those ideas, and those will be very helpful to study the next things we are going to study, basically the high-energy spectrum and stuff, right? Okay. The first thing discussing here is actually kind of an idea came by the put forward by actually the Max Planck. The scientist Max Planck came up with a very important idea at the start of the 20th century, right? Actually at the 1900, right? Year 1900, right? He came up with a revolutionary idea. Let's discuss about that thing. The point is this. He said, this is the Max Planck's idea, right? The Max Planck's idea, right? It is better. First we'll write the idea and then we'll discuss. First we'll write the idea of the Max Planck, then we'll have the discussion, right? Okay. Let's try this. The point is this. This point is given in a note like this. In 1900s, a German physicist Max Planck proposed that energy is quantized. Energy is quantized, right? That wording is there in your book, right? Just write this thing. After that, just write this thing with the inverted commas in red color. Just write this one. After that, I'll explain what it says, right? Okay, just write. Put some inverted commas and write. in red color, right? Energy can be either released or absorbed. Energy can be either released or absorbed. Energy can be either released or absorbed. By atoms. Energy can be either released or absorbed by atoms only in discrete quantities. Continue the statement with the red color, right? Energy can be either released or absorbed by atoms only in discrete quantities. Of some minimum size. Only in discrete quantities of some minimum size. Close the inverted commas. Of some minimum size, close inverted commas, right? The point is this, right? Okay, this kind of thing, right? See, the point is this, right? So Max Planck came up with this kind of a new idea. Let's think of atom. This is the simplified idea of the Max Planck, right? Atoms can absorb radiation. Atoms can emit radiation. Atoms can absorb radiation. Atoms can emit radiation like this. Right? Actually, these waves, radiation waves, right? Actually, now waves. What are waves? First of all, let's discuss about what are waves. Right? What they do? Waves. What they do? Any idea? Yes, Chris? Yeah. What we are mentioning as waves and what they are doing? Waves. Yeah, waves are ones which carrying energy from one place to another place. Waves are used to carry the energy. Those are the waves, right? Okay, the simplest idea, right? So those energies can be absorbed or emitted as waves by atoms, right? Only in discrete quantities of some minimum size. That is what Max Planck said. It is like this, Laman. So you can absorb energy, you can release energy, right? With some discrete quantities. See, let's say you are releasing some energy with 6 joules of energy, right? Some 10 joules of energy, 6 joules of energy, say 2 joules of energy. So atoms can emit radiation. Like this. Atoms can emit radiation. And atoms can absorb radiation as well. Atoms can absorb radiations. Right? Atoms can absorb radiation as well. Let's see, some radiation is absorbed. Atoms can absorb radiation, waves. Atoms can emit waves. Atoms can absorb energy. Atoms can emit energy. Right? In discrete quantities, with some minimum energy. That is the idea. With some minimum energy, right? That minimum energy is referred to as the quantum. Right? So Max Planck came up with the concept of quantum. This is the born of the quantum concept. So if you are to see this picture, this atom had absorbed this kind of energy, release this kind of energies. This is the minimum quantity. So we can refer to the smallest quantity of energy. smallest quantity of energy as quantum. This is the idea, the quantum idea. This is kind of a revolutionary idea, and actually this idea is not a surprise at that stages. Why is that? Because Lamai, at the start of the 19th century, right? Dalton came up with a revolutionary idea. No? What was that? That was actually the atom or the mass. The atom or the mass is with a fundamental unit. The property mass is with a fundamental unit. The tiniest uncuttable indivisible unit, which was known as the atom at those ages. Nowadays we know that is not true. Anyway, that concept, mass is with a uncuttable indivisible tiniest unit, fundamental unit, which is the atom according to that age. But the concept is the thing here, right? Then Stoney came up with another idea. The property charge is also with such a uncuttable, indivisible, right, unit, tiniest unit, the fundamental unit, which was the electron. Charge is with a fundamental unit, the electron. And now Max Planck said that energy of waves is also with a fundamental unit, right, of some smallest quantity, the smallest tiniest quantity, which is the quantum. The same logic appearing, right? For the mass, it was the atom with the Dalton. Nowadays we know that is not true. But with the charge, it was the electron. The idea came up with the Stoney. Now, for the energy, property energy, the tiniest, right, smallest unit of radiation energy is quantum, right? That is the idea. So, that idea came up with Max Planck, the quantum idea. This was the born of the quantum mechanics, quantum science, right? So, that is the simplest idea. I think you got the idea clearly, right? So, we'll write the stuff, right? We'll write the stuff, and then we'll continue the discussion, right? Okay. Then write this thing as well at that space, right? Planck gave the name. Planck gave the name. Write it in red color. Quantum. See, quantum. This one, quantum. Planck gave the name quantum. Within brackets, come to the normal color and write. Within brackets, meaning fixed amount. Close the brackets. Now I put some inverted commas with the fixed amount. Put some inverted commas, right? Close the brackets. To the smallest quantity of energy. That can be emitted or absorbed as electromagnetic radiation. Planck gave the name quantum, meaning fixed amount, to the smallest quantity of energy that can be emitted or absorbed as electromagnetic radiation. Right? As electromagnetic radiation. Right. At the next line, just write. he proposed at the next line, just right, he proposed, put a comma, he proposed, comma, again come to the next line, just right, if the energy of a quantum is equal to capital E, if the energy of a quantum is equal to capital E, right, if the energy of a quantum is equal to capital E, then right, you can write this equation, Lamai. Then that E, the energy of the quantum, is equal to h mu, right? So just write the equation. Right? So this E is the energy of a quantum. Energy of a quantum. Smallest energy unit, right? And h is the Planck constant. It's a constant value, as Planck was the scientist who came up with this equation. It is honored, this constant is honored as the Planck constant. Right? It is with a fixed value, right? Constant value, it is a fixed value. This value will be given in your exam paper, but just remember this value, it will be useful. Like the c value, the speed of light is equal to 3 into 10 to the power 8 ms minus 1. Just remember this value as well. That was the Planck constant, right? And mu is the frequency of the radiation. Mu is the frequency of the radiation, right? This one is actually frequency of electromagnetic radiation. Right? So you can write this equation, Lamai. Write this equation. Energy of a quantum, Planck constant, and the frequency of the electromagnetic radiation. So actually this equation is also a two variable equation, Lamai. Even though still you see this one also as a 3-term equation, 1, 2, 3 terms are appearing, still this is also a 2 variable equation. This is also a 2 variable equation. See, this is always a constant, no? This is always a constant, no? Only 2 variables are there. The frequency of the electromagnetic radiation and the energy of the electromagnetic radiation, right? Only 2 variables are there, right? If you know the E, this equation can be used to come up with the mu. If you know the energy of the quantum, you can use this equation to come up with the frequency of the electromagnetic radiation. Or if you know the mu, you can use this equation to come up with the energy of the quantum, right? So this is just a 2 variable equation, even though you see this as even though you see 3 terms are appearing. 2 variable equation, because this is always a constant, right? If you know this, you can come up with this. If you know this one, you can use this equation to come up with this, right? So another 2 variable equation. Actually, one can say this is the relationship between the energy and the frequency of the electromagnetic radiation. This is the relationship between the energy and the frequency of the electromagnetic wave. Energy and the frequency. Energy of the quantum and the frequency of the radiation, right? That is the relationship between those two. Because h is always a constant. Right? When we are doing the problem solving stuff, I'll explain that thing again, right? Okay. That is how you would see this equation. This is just a two variable equation. If you know the E, you can use this one to come up with the mu. If you know the mu, you can use this one to come up with the E. This is the relationship between the energy and the mu, right? Energy and the mu. Energy of a quantum and the mu. Energy of the tiniest, smallest energy unit and the frequency of the radiation. The relationship between those two is given by this equation, right now? Okay, got the idea? That is the idea, right? So it's the Planck said atoms will absorb electromagnetic radiation, atoms will absorb energy as electromagnetic radiation, and atoms will emit energy as electromagnetic radiation, but in fixed amount, and the tiniest, the smallest of those fixed amount is referred to as the quantum. That is the idea. Right now? Okay, that is all about the quantum concept. So the first idea of quantum is came by Max Planck in 1900, right now? Okay, right, that is some special idea, right? Then comes the turn of the Albert Einstein. Lamai, let's discuss a bit about Albert Einstein, right? Such a wonderful scientist, right? Now, actually, who is the most famous scientist? Who is the most famous scientist in the world? Yes, any idea? Who is the most famous scientist in the world? You can search for Google. AI will give you the answer. I wish this would be the answer. Yeah, Chris, any idea? Who is the most famous? Yeah? Einstein. Okay, everyone knows Einstein. Even though the people don't know what he has done, or what he has given to the world, even though people won't know that thing, still they know the name of him. Albert Einstein is the most famous scientist in the world, right? So surely AI should give that, right, with the Google, right? Okay, so okay, then let's keep it to a side, right? Then tell me, what is the most famous equation in the world? This is some scientific stuff, right? What is the most famous equation in the world? Anyone? Yes? Uthuni, you can come up with the answer. Do you know what is the most famous equation in the world? Can you use the chat box, or even the Chris can answer that question? Only you two guys are there, right? Yeah. What is the most famous equation in the world? Yeah, no idea, right? No. Can we check that thing? It should appear, right? Let's check that thing. I don't know whether it gives you the idea, but according to scientists, yeah, most famous equation in the world. Oh, is it there at the Google?
Yes.
Oh, right. Then no worries. Yeah, Google, the AI guys are giving you that equation. E is equal to mc squared. That is the most famous equation in the world, right? Who is the one came up with that equation? Einstein. Actually, Einstein had a, right, we say, right, he had a wonderful year, right, yeah, which is actually the 1905, right, that was referred to as the Einstein's dream year. It is referred to as the Einstein's dream year, right? So 1905. In that year, Einstein came up with 4 new concepts, some 4 new revolutionary ideas, were proposed by Einstein at that year, right? So Einstein's dream year, right? The scientific community, the community, got to know about the Einstein in 1905. One equation is that E equals mc squared. I'll discuss about the E equals mc squared bit, right? Yeah, some stories are there with the E equals mc squared, right? So that is the most famous equation, right? Anyway, let's discuss a bit. Yeah, just starting. It's all about science, no? Right? E equals mc squared. Do you know anything about the E equals mc squared? Anything about E equals mc squared? Yes, Chris or Ivadutuni? Energy, yeah, it's the mass and energy relationship. mc squared, E equals E and the m is there, yeah. So, any other things? That was the equation Lama actually led to the atomic bomb. Okay, some negative stuff, right? That was the equation responsible for the atomic bomb, right? Then Einstein won't be able to get any credit as a Nobel Prize for the E equals mc squared, even though that is the most famous equation in the world, right? Einstein got only one Nobel Prize in his life. That is not for the E equals mc squared, and that is not for the general relativity. That is not for the general relativity. That is not for the relativity or the general relativity, which is the other most famous work of the Einstein. When it comes to Einstein, what he has done is E equals mc squared, one thing. The second thing, another thing is the relativity concept. With the relativity concept, they came to know about the Einstein, right? When you are to go to the university, you will learn about that thing, relativity concepts. In A levels, normally you are focusing about the Newtonian mechanics. The second unit, you may have started with the physics, Newtonian mechanics, right? But the relativity is the most important stuff there, right? So that will be learned in not in A levels but in the campus, right? So Einstein is the one who put forward the ideas of the relativity, right? So Einstein won't got the Nobel Prize for the relativity either, not for the E equals mc squared. Anyone knows to which Einstein got the Nobel Prize for? Basically, Einstein was unable to get the Nobel Prize for the E equals mc squared because of the disaster it done to the world, right? Okay, to get the Nobel Prize, that work should be identified as a work which led to which helped to improve the qualities of the mankind, right? To get a Nobel Prize, that is what Nobel site says, Nobel www.nobel.org says, right? To recognize a work as a work to get the Nobel Prize, that work should be benefited to the mankind. Only for works which benefit to uplift the life of mankind, you get the Nobel Prizes, right? So Einstein would never be able to get the Nobel Prize for the E equals mc squared then, right? It was a disaster ultimately, right? Okay, it had a disaster, right? But nowadays the E equals mc squared is used to come up with the nuclear reactions, right? Nuclear power plants and the energies are produced from with that, but he was unable to get the Nobel Prize because of that disaster which started all the stuff, right? Okay, so Einstein got the Nobel Prize, not for the E equals mc squared, not for the general relativity. All the guys we know, all the guys know about the relativity and the Einstein, right? But not for those stuff, the Einstein got the Nobel Prize, but for some concept called as the photoelectric effect. Photoelectric effect. For that, Einstein got the Nobel Prize in 1921. Yeah, 21, right? For the photoelectric effect. Actually, now we are going to discuss about that stuff. The photoelectric effect comes up with this equation, same equation, E is equal to h mu, right? That explanation came up with this same equation, the Planck's equation, right? That is stuff now we are going to discuss about, right? Before we are discussing that thing, let's talk a bit about the E equals mc squared, right? That is the famous equation. If you don't know about that thing, that is not good, no, right? As people, you doing science, right here, right? So yes, when I first asked about this thing, okay, yeah, for law of photoelectric effect, yeah, that is for what the Einstein got the Nobel Prize, right? Right. So when I asked you the question, what that E equals mc squared means, right? You said that yes, this is the relationship between the m and the E, mass and energy, right? I'll give you the idea more clearly about the mass and energy stuff, right? Okay, this is what E equals mc squared means. This is what E is mc squared means, right? Okay, the idea is this, right? So E is equal to mc squared. Let's discuss about that idea, right? Of the equation squared. Lamai, this equation says actually, right? Mass is the condensed energy. Mass is the condensed energy. That is the idea of this equation. Mass is the condensed energy. I'll explain that thing to you. Mass is the condensed energy. See? Let's see what it means. Let's calculate the energy in a 1 gram of mass. In a 1 gram of material, let's try to come up with the energy inside that thing. 1 gram of material. 1 gram of material. Very small particle. Inside that, let's calculate the energy. E is equal to mc squared. So E is equal to the mass. 1 gram is. So basically, for these equations, we have to apply the stuff with the SI units. SI units. So 1 gram means 10 to the power minus 3 kilograms. 1 gram means 10 to the power minus 3 kilograms. C squared. C means the light speed. That means 3 into 10 to the power 8 ms minus 1. You have to come up with the SI units. Squared. This means you are coming up with 9 into, you have 10 to the power 16 here. You have minus 3 here. 9 into 10 to the power 15 joules. As we are substituting with the SI units, the answer will come up with the SI units. In other words, this gives you in kilojoules 9 into 10 to the power 12 kilojoules of energy in a 1 gram of material. In a 1 gram of material, you have this amount of huge amount of energy. Right? This is what this equation says. Mass is the condensed energy. Mass is the condensed energy. It is like this, Laman. So mass is the condensed energy. Condensation, you know the stuff about the condensation. You know the gases. You know the liquids. And you know the concept of condensation. Right? When gases convert to liquids, right, or when gases convert to solids, you say condensation. Concentrating, gas converts to solid, so gas is like this. So gas is like this. Gas is like this. Solid is like when the gas, all the particles are condensed. This is how the solid looks like. This is gas. This is solid. This is the condensation. Actually, mass is the condensation of the energy. right? The same concept, right? So when it comes to waves, waves are like this, carrying energy. Waves spread throughout the space. Waves spread throughout the space, carrying some energy. If you were to condense this wave, you will come up with the mass. You will come up with the mass. If you were to condense this stuff, you will come up with the mass. Mass is the condensed energy. If you were to put this thing like this and condense the stuff, you will come up with the mass. Mass is the condensed energy. That is what this equation says. It's a very important equation. With a very little mass also, you can think of very high condensed energy. Right? Very little space. Very little space. More mass is there when it comes to a condensation concept. So the same logic appears here. With a little space, more energy is there. Condensed energy. Solid is condensed mass. So in energy terms, this equation says mass is condensed energy, right? That is the usage, that is the view of this equation, actually, so that we can use this very little amount of grams even to produce huge amount of energy there, because in this thing the huge amount of energy is condensed. So we can use that huge amount of energy to do some work. That is what we do with the nuclear reactions, right? Nuclear power plants, right, and the stuff. That is what we do, right? So that is this is the equation. This was the same stuff led to the atomic bomb. Very huge amount of energy is there inside very little amount of mass, right? So that is the idea of the equals mc square, right? So that is about the most famous equation of in the world, right? So we'll stop that discussion from that point, right? So just to know that, right? So as you are some students who do in the science, right? That is about the world famous equation, right? Okay, right. Then we'll come up with Einstein's idea. In 1905, I said he had came up with 4 revolutionary ideas. One thing is this, equals mc squared, right? Another thing is photoelectric effect. That is what we are going to discuss now. And the relativity generality, that is the thing which Einstein introduced to the world, relativity concepts, right? And the fourth thing is again another concept is there known as the Brownian motion, right? Those 4 concepts are actually revolutionary concepts, right? Actually changed the direction of science with those all the 4 concepts, right? So such a wonderful year, right? Such a dream year for Einstein, right? So let's discuss about Einstein's work with the electromagnetic radiation, right? Okay, Einstein, right? This is in 1905, right? Albert Einstein. Albert Einstein, right? Okay, he came up with the concept of photons, not the protons, but the photons. Let's discuss about that idea. The concept of photon, right? Okay. The idea is this, Lamai. The idea is this, right? He said, the point is this, I'll come with the idea. The idea is this. So Max Planck said like this, no? Max Planck said, right? Max Planck said that energy released by waves is with the smallest quantity, no? Which is known as the quantum. That Einstein said, let's say the quantum is 2 joules. He said, actually this quantum is actually an energy packet. He said this quantum is actually energy packet like this. So this joules is kind of energy packet. You have one energy packet here with 2 joules. That is why this wave carries some 2 joules of energy. And Einstein said, as this wave carries 10 joules of energy, he said this wave is with 5 energy packets. That wave is with 5 energy packets. So that it is able to carry 10 joules of energy. The smallest quantity into 5. Then 10 joules. This wave carries 3 energy packets. 3 energy packets. So that 6 joules are generated. So energy of energy packet can be calculated with the use of the same equation. Energy of the energy packet can be calculated with the use of same equation. If the energy of a energy packet or the photon, it is known as photon. Energy packet is known as a photon. So if the energy of an energy packet or the photon is equal to E, then you can say energy of a photon is equal to h mu. That is the Einstein's idea. He actually developed the Planck's theory. And he came up with kind of a particle nature to the wave. He gives some particle nature to the wave. Particle nature to the wave. So waves means waves are not with any particle nature. We can't touch the waves. No particle nature there. But when it comes to matter, the particle nature is there. So what Einstein did was, he introduced some particle nature to the wave. Some particle nature to the wave. Energy packets. Right? So it is kind of an imaginary idea. Still you can't touch the wave. But he said, the energy of a wave is carried by stream of energy packets. Stream of particles. Smallest, tiniest particles. Energy packets. The photons. He named those energy packets as photons. So energy of a wave is carried by energy packets. Photons. Right? So smallest quantity, he said it is the photon. Energy packet, photon. That was the idea by Einstein. He said energy of a wave is carried by energy packets, photons. Right? So if you know the energy of a photon, then multiplying that energy with the number of energy packets, you can get the energy of the total wave. And the energy of photon is given by the same equation, which is given by the Planck. That is the total idea here. Right? Okay. Let's write the stuff, Lamai. Let's write the stuff and then discuss a bit more. Right? Okay. This is about the next point. Right? This is about the next point. Right? It says like this. In 1905, Albert Einstein extending the Planck's quantum theory, this was there in the note, right? Deduced that the radiant from a metal surface behaves like a stream of tiny energy packets. Radiant from a metal surface are also with atoms, right? Metal surface are also with atoms, right? So it says, right, radiant energy from metal surface behaves like stream of tiny energy packets, right now? Okay. Just write like this, Lamai. Next, at the next line, just start writing like this. Each, come to red color and write, energy packet, each, in red color and write, energy packet, come to the normal color, which is like a, again in red color, particle of energy, which is like a particle of energy in red color, particle of energy. Put some inverted commas to the particle, that word particle, which is like a particle of energy. Put a comma, come to the normal color, is called a is called is called is called is called again red color photon. Photon. It is not the proton, right? It is a photon. It's called a photon. It's called a photon. It's called a photon. Right? Okay. Then write this one, right? Don't need to draw in this one. I'll give you a more clear picture than that. So if the energy of a photon is equal to E, or a photon is given by, let's say, right, is given by E, right? Just right. If the energy of a photon is given by E, so the same equation appears. Energy of a photon is equal to Planck constant into frequency of Friedmann radiation. Right? So you can draw this one even. So this is the simplest idea. If you take the wave like this, right? This wave is made out of. So let's say, if you have to think of the wave like this, this wave is, you can say, made out of some stream of energy packets. Right? So energy of one energy packet is actually given by this equation, E is equal to h mu. That is the idea. So first write this one and then this picture as well. If the energy of a photon is given by E, the photon is equal to Planck constant frequency of radiation, then have this picture as well, small picture. First write this one, Lamai. Then write this, draw this. Right? Actually, with this picture, we can say this thing as well. Then energy of electromagnetic radiation. Energy of electromagnetic radiation, if it is given by En, if that is to be given by En, if that is to be given by En, that is equal to energy of a photon into number of photons, energy of photon into number of photons will give you the energy of the total wave, right? These are actually, right? Is equal to number of photons into energy of a photon. Right? Now here the n is kind of a positive integer. N is kind of a positive integer. This is the number of photons. You can't have half of photons, right? You can't have half of energy packets, right? Always it's an integer number, right? This is the tiniest energy unit. Got the idea, no? The tiniest uncuttable indivisible energy unit. Photon. Photon. You can't divide this. You can't divide this to halves. You can't divide this to any portions. This is the tiniest uncuttable indivisible energy unit, the fundamental energy unit, the photon. See, all these things are related to each other. The fundamental energy unit, the photon, right, as an energy packet. So this idea is very revolutionary idea. Why is that? Because with this idea, Einstein was able to give some particle nature to waves. Give some particle nature to the waves. With this, Einstein was able to give some particle nature to the waves. Complete, no? Just quickly write, Lama. Lama, I need some 10 minutes, right, to complete this section, right? Actually, it is my fault, right? I was late for 10 minutes, right? So let's complete this one, right? So that we can start the next class with the hydrogen spectrum and the stuff, right? So meet some 10 minutes, right? Okay. So be with the class, right? For another 10 minutes, right? Okay. This is clear, no? So you can take a screen capture, Lama. Take a screen capture. Right. Then we'll discuss the next idea of the electromagnetic waves. Right. First we have discussed about the relationship between the three properties, the speed, frequency, and the lambda. Then we have discussed about the Planck's idea, and then the Einstein's idea, who came up with some particle nature to the waves. Next, we'll discuss about the de Broglie's idea. De Broglie's idea. De Broglie came up with a special idea. So, Lama, at those ages when de Broglie said this idea, right? Actually, Einstein is kind of a famous scientist, right? Einstein marked his name earlier before de Broglie, right? De Broglie said like this. De Broglie said, look, if you can accept the Einstein's idea of waves behaving as particles, this is what de Broglie said. Look, if you can accept the Einstein's idea of waves behaving like particles, then you have to accept my idea as well. What is his idea? He said, okay, if appropriate conditions, waves can behave as particles, then the particles like electrons should also can be considered as waves. Or the particles like electrons can also act as waves. So you have to accept my idea as you are accepting the Einstein's idea. That was the de Broglie's logic. And not only saying that, that particles are also having some wave properties, not only saying that, he came up with an equation proving that idea. He came up with an equation, de Broglie came up with the equation to prove that idea. What is the idea? The particles are also having some wave properties. As you are accepting the Einstein's idea of waves are having the particle properties, now you have to accept my idea as well. I am saying that particles are also having wave properties. I am not just saying that, I am proving that idea with a equation as well. That is what de Broglie said. He came up with the equation, right? He came up with the equation. So what was the equation? His equation is this, right? The wavelength is equal to h over p. This was the de Broglie's equation, very important equation. This says actually the lambda, the wavelength, here the momentum, right? So lambda is the wavelength, this is the momentum. To have a momentum, you should have a m and a v. To have a momentum, you should have a m and a v. So having a mass means you are dealing with a particle. You are dealing with a particle. So momentum gives you the particle nature. With this equation, the momentum gives you the particle nature. The wavelength gives you the wave nature. So he said that, right, if you are to have a momentum, definitely you should have lambda. That is his conclusion. If you are to have momentum, we know that electrons are with momentum, right? With cathode ray experiments, that is proved with the right paddle wheel thing, right? Electrons are with momentum. So he said, if you are to have a momentum, you should have lambda. You should have lambda. So it is like this now. P is equal to h over lambda. Hurry. If you want to have a momentum, you should have a non-zero lambda. Non-zero lambda. If it is zero, this becomes infinity. If this is zero, this becomes infinity. Right? That means, right? That means it is not acceptable, right? If you are here zero, that is infinity, not acceptable, not defined then. So he says that if you are to have a value for here, some calculated value for here, which is not the infinity, it is not giving you any definition, no? any idea. No? If you are to have a value for momentum, he is saying that lambda should not be the zero. Non-zero lambdas will lead to some acceptable values for p. So he said that to have momentum with electrons kind of stuff, you should have lambda with that, lambda appearing with that. That means to have some particle properties, should have some wave properties too. Right? So that is the idea. So he came up with this equation, right? So this is not hard to prove. We'll prove this thing, right? Before this, just write the stuff. We'll write the stuff, and then after that we can prove. Very simple proving is there, right? Just quickly write this stuff, Lamai, to complete the note, right? First point it says, right? First we'll go to the note, what it says, and then we'll continue. The note says, Louis de Broglie extended the idea that if radiant energy could, under appropriate conditions, behaves as a stream of particles or photons, matter under appropriate conditions possibly would show the properties of a wave. That is what de Broglie said, right? Let's continue with that. Just write. De Broglie suggested that an electron moving about the nucleus of an atom, just write down. An electron moving about the nucleus of an atom behaves like a wave and therefore has a wavelength. Right? At the next para, just write. He proposed that the wavelength of an atom, sorry, the wavelength of an electron, sorry, the wavelength of an electron, he proposed that the wavelength of an electron within brackets or any other particle, he proposed that the wavelength of an electron within brackets or any other particle close the brackets depends on its mass and velocity, depends on its mass and velocity, so that the momentum, right? You can write this one, right? And this concept is referred to as the wave particle duality of electrons. This concept is referred to as the wave particle duality of electrons. It's referred to as the wave particle duality of electrons. Just write that thing as well, right? It says, now I just continue writing. Electrons are with both the wave and particle properties at the same time. At the same time means simultaneously. Right? Put that thing as well. This is referred to as the wave particle duality of electrons. Right? So at the same time, you are with both the properties. When you show in the momentum, you show the lambda as well. When lambda is there, at the same time you have momentum. To have a lambda, you should have a non-zero momentum. If the momentum is 0, lambda is infinity. That means, right, not defined, right? To have a measurable lambda should have non-zero momentum. So momentum and lambda appears at the same time. That means particle property and the wave property appears at the same time. At the same point, both the properties are there. That is the idea. Right? Wave and particle properties are appearing at the same time. Right? So it's kind of normal stuff, right? It's not a hard stuff. It is kind of normal stuff, right? It is not a new thing to grab, right? So let's see. The practical example is this. Let's say, right? So let's say Shiranti is there. This is the idea. Shiranti is there. Right? And see, Mahinda and Namal is also appearing. This is Namal. This is Mahinda. This is the concept, right? Simply in terms. Shiranti is there. Actually, Shiranti is Namal's mother. To Namal, she is the mother. To Mahinda, she is the wife. So Shiranti shows both the properties at the same time. If Namal and Mahinda are in a quarrel, right? So in a kind of a argument, the Namal and Mahinda, Shiranti will act as a mother as well as a wife. At the same time, the Shiranti is showing both the properties. So if Shiranti can do so, why can't the electrons? The idea is very simple, na? That is not a hard stuff, right? That is the idea. So both the properties are shown at the same time, right? Concept is that. Very simple idea, right? But the thing is, only for those special scientists, they can relate the same idea with electrons as well. That is the idea, right? That is the case, right? Okay, that is all about the stuff, right? And proving this equation is nothing, Lamai. I'll write that thing as well. It is nothing, right? Proving this one is very simple, right? So I'll prove that thing and conclude lesson, right? The proof is this. Deduction is very simple. So we know the E is equal to mc squared, and we know the E is equal to h mu. This is from Einstein. This is from Planck. So if you have to equalize these two, mc squared is equal to h mu. So mc is equal to h mu over c. But we know that mu over c is actually 1 over lambda. With the first equation, no? C is equal to mu lambda, no? C is equal to mu lambda, so mu over c is 1 over lambda. That gives you, right, mc is equal to h over lambda. That mc is p. mc is p. mc is your momentum. Mass into speed, mass into speed, it is the momentum. Mass into speed, it is the momentum. So momentum is equal to h over lambda. So the lambda is equal to h over p, right? So derivation is very simple, right? Not much hard. It could be done like this. mc means the mass into a velocity. That is actually momentum is h over lambda. So lambda, if you have a subject lambda, you get this one. Right now, so that is all with the deep Broglie story. So this is actually giving you the wave particle dual nature of the electrons, right? Okay, so with the next lesson, Lamai, just to complete this one, I have a screen capture. With the next lesson, we'll do some numerical calculation stuff, right? Regarding these equations we have learned. E is equal to h mu, the c is equal to mu lambda, right, and the E is equal to HCO lambda stuff as well, right? So we'll discuss about few more calculations, and then we'll can do the discussion of the hydrogen spectrum next day, right?